We're going to look today at another way of applying the formulas that we had for the sine or cosine of a sum of angles in order to get some formulas that allow us to transform a sum of functions into a product, or vice versa. These are known as the product to sum and sum to product formulas. So let's imagine that we wanted to get an expression involving a sine alpha plus sine alpha times a sine beta. Let's say we've got this sort of situation. We've got two trigonometric functions of different angles, and we want to find a new way of expressing them. Well, one way that we can get at that is in the following way. We can look at the formula for the sum of sine of a sum of these angles and sine of a difference of these angles, and we'll be able to use some algebra to get a new way of expressing things like this, like sine alpha, sine beta. So let's look at what we get and see what sort of formulas we can come up with. If we look at sine of alpha plus beta, we know that this is sine of alpha times cosine of beta plus sine of beta times cosine of alpha. And we know that if we take sine of alpha minus beta, that's going to give us sine of alpha cosine of beta minus sine of beta cosine of alpha. These are our standard formulas for sine of a sum or difference. Now, the thing that we're going to take advantage of is the fact that these two terms appear with opposite signs in these two expressions. So what we are going to do is we're going to subtract these equations, we're going to add these equations to one another. We're going to take sine of alpha plus beta, add it to sine of alpha minus beta, and those two terms at the end, the sine betas, cosine alphas, are going to cancel out. So let's see what happens when we do that. If we add the left-hand sides of these equations together, we get sine alpha plus beta plus sine alpha minus beta. And on the right-hand side, we have sine alpha cosine beta, that gives us 2 sine alpha cosine beta, and then plus 0 because we have plus sine beta cosine alpha from the first equation and minus sine beta cosine alpha from the second equation, which are going to cancel each other out. Now, we have an expression in a similar sort of form to what we had above, sine alpha, sine beta, only this is sine alpha cosine beta. And now, if we divide both sides by 2, what we get is that sine of alpha times cosine of beta for any angles alpha and beta is always equal to, and I'll write it with the 1/2 out in front, 1/2 of sine of alpha plus beta plus sine of alpha minus beta. And this is what we call a product to sum formula, because we start on the left-hand side of this equation with a product of two expressions, and we write an equivalent form on the right that involves a sum of two expressions. So this allows us to transform back and forth to identify certain identities that occur. So this is one of our product to sum formulas. In order to get the other ones, we're going to want to use the cosine formulas, cosine of alpha plus beta and alpha minus beta. So let's look at how that goes. If we have cosine of alpha plus beta, that is, we know, cosine of alpha times cosine of beta minus sine of alpha times sine of beta. And we have that cosine of alpha minus beta is equal to cosine of alpha, cosine of beta, plus sine of alpha, sine of beta. Once again, notice that the last term on the right in the two equations are exactly opposite of each other, which means that we can again add these two equations and get that cosine of alpha plus beta plus cosine of alpha minus beta is equal to 2 times cosine alpha times cosine beta, and then again plus 0, because those two terms on the right-hand side canceled out. And so rearranging this again, we get that cosine of alpha times cosine of beta for any alpha or beta is equal to 1/2 times cosine of alpha plus beta plus cosine of alpha minus beta. So this gives us a couple of different kinds of expressions that we can look at. We looked at sine of alpha times sine of beta. We got a formula for that on the last page. Here we've gotten a cosine alpha times cosine beta here. The last thing that we want to do to get a sine alpha times sine beta, a product of two sine functions, is we want to take these cosine functions again, but now we want to subtract them. If we take cosine of alpha minus beta minus cosine of alpha plus beta, look at what that's going to give us. So cosine of alpha minus beta, we know, is cosine of alpha cosine of beta minus sine alpha, plus sine alpha sine beta. And we're subtracting cosine alpha cosine beta minus sine alpha sine beta. So now when we distribute the negative through, the two terms that involve cosines, the cosine alpha, cosine beta, are going to cancel. We've got a positive one from the first set of parentheses minus the one in the second set of parentheses. So those are going to cancel out. And then for the sine terms, we've got a sine alpha sine beta on top minus a negative sine alpha sine beta. So that gives us 2 of those sine alpha sine betas. So we get that sine alpha times sine beta is equal to 1/2 times cosine alpha minus beta minus cosine alpha plus beta. So with these three expressions here, we're able to transform any product of two sines or cosines of any angles at all into an expression involving a sum of sines or cosines. Let's summarize all these here, and let's try and put it in a form that makes it easy to memorize. So our product to sum formulas are we have that sine alpha sine beta is equal to 1/2 times sine. Now I'm actually going to write it this way: sine alpha minus beta plus sine alpha plus beta. And I'm doing this so that we can keep things consistent throughout the whole thing. I'm sorry, and I miswrote that first line. This should be sine alpha cosine beta. That was the first one we did. Then if we have cosine alpha times cosine beta, this is going to be 1/2 times cosine alpha minus beta plus cosine alpha minus beta. And if we have a sine alpha times sine beta, this is going to be 1/2 times cosine alpha minus beta minus cosine alpha plus beta. That should have been an alpha plus beta last in the second line. Sorry about that. It's correct now. So if we set things up this way, we can see that there are some patterns which help us in memorization. So first of all, the 1/2 are the same in all of these expressions here. And if we set it up the way that we have here, we always have a sine or cosine of alpha minus beta plus or minus a sine, the same function of alpha plus beta. And so we can see that if the two functions that we're working with are different, sine alpha and cosine beta, then we're going to use sines in our formula. If the two functions are the same, we're going to use cosines. Now, if they're the same and they are both cosines, that's going to give us a plus. And if they're the same in both sines, that's going to give us a minus in the middle of the expression. Notice this is consistent with a lot of the things that we've seen so far in our identities. A lot of times the identities that we have for sine, like the half-angle identities, for instance, involve negatives, whereas the corresponding formulas for cosines involve positives. Although this isn't universal, so you still need to put in the work to memorize the individual expressions that we've got. All right, so this can allow us to take a complicated expression, complicated in the sense of having things multiplied together, and turn it into an expression involving things added. And as I've alluded to before, when we go to calculus, it's going to turn out that sums and differences of functions are much easier to work with than products. And so having a way to turn a product of functions into a sum or difference of functions is actually quite effective. So let's see an example. Let's express sine of 4x times cosine of 3x as an expression, or I should say as a sum or difference of individual functions. That is not multiplied by each other. So we look here, we've got sine 4x times cosine 3x, and we remember the formula. We know that if we have sine alpha times cosine beta, that is going to be 1/2 times. Now, because the two functions are different, this is the way I remember it, because the two functions we're working with are different, that means that we're going to be dealing with sines. We know that the angles that we work with are always alpha minus beta in the first place and alpha plus beta in the second. And when we're dealing with sines, it's always plus inside. So this becomes 1/2 times sine of, now alpha here is 4x, beta here is 3x, and so 4x and 3x get added together over here. So we have that sine of 4x times cosine of 3x is equal to 1/2 times sine of 7x plus sine of 3x, I got ahead of myself, or just sine of x rather. Sine of x plus sine of 7x. And so we managed to turn an expression involving a product of trigonometric functions into an expression involving a sum of trigonometric functions. And that's really all there is to it. The only difficult part of this process is memorizing the formulas. So let's do one more example, and then we'll look at an application of this that winds up being very useful for things that we're going to be working on in solving equations. So let's express cosine of 3x plus 2 times cosine of 5x as a sum or difference of individual functions. Of course, we're going to follow the same thing. We've got cosine of some angle. The fact that it's an algebraic expression doesn't make any difference. Times cosine of some other angle. And we're going to write that using the formula from before. Now we have that cosine of alpha times cosine of beta. We know that's going to be 1/2 times. Now cosine, we got cosine and cosine, so those are the same. Which means that we're going to have a cosine of alpha minus beta and a cosine of alpha plus beta. And then because the two functions that are the same are cosines, we've got a plus in between. So in this problem, alpha is 3x plus 2, and then beta is 5x. So we get 3x plus 2 minus 5x plus cosine of 3x plus 2 plus 5x, which simplifies down to the expression 1/2 times cosine of negative 2x plus 2 plus cosine of 8x plus 2. And that's really all there is to applying these formulas. Excuse me. Now, the next thing that we want to do is to basically go the other way. We want to find a way of taking a sum of trigonometric functions involving different angles and express it as a product. Now, the reason why we want to do this typically is because it's a lot easier to solve an equation when you have a product of things that is 0. So if you can work out your problem to be a product of a bunch of things equaling 0, well, then you can take each one of the factors and set them equal to 0, which makes your problem a lot easier. And so let's look again at this sine alpha cosine beta situation here. So we have the formula sine alpha cosine beta is equal to 1/2 times sine alpha plus beta, sine alpha minus beta rather, plus sine alpha plus beta. And this is our formula. But let's suppose that we wanted to somehow work with an expression like sine of theta plus sine of sigma. Let's say that we had two sine functions that we wanted to add together, and we wanted to express this as a product. We want to express this as some sort of product. So our formula from before takes a product of things and turns it into a sum of things. In theory, we should be able to undo this process and turn a sum of things into a product of things. So let's see if we can do that. If we take our formula here and multiply both sides by 2, then we could write it as sine of alpha minus beta plus sine of alpha plus beta equals 2 times the sine of alpha times the cosine of beta. So if we can somehow match up these expressions right here, if we can find an alpha and beta that give us alpha minus beta equaling theta and alpha plus beta equaling sigma, then we'll be able to make this formula work. So what we want to do is we want to find alpha and beta such that alpha minus beta equals theta and alpha plus beta equals sigma. Well, here we can actually solve for alpha and beta using almost the same sort of process where we came up with the formula in the first place. We really are just untangling the equation, the formula that we have above. So if we take alpha minus beta equals theta and alpha plus beta equals sigma, and we add these two equations together, then we'll get that 2 alpha is equal to theta plus sigma. So alpha will have to be equal to theta plus sigma over 2. Okay? So then that means that beta has to be theta, or has to be alpha minus theta, rather. But we worked out from before that theta has to be alpha has to be theta plus sigma over 2, which means when you work it all out, beta has to be sigma minus theta over 2 when you simplify all that expression down. So, if we have alpha being theta plus sigma over 2 and beta being sigma minus theta over 2, then we have that sine of alpha minus beta is equal to sine of theta, because alpha minus beta is equal to theta, and we have sine of alpha plus beta equals sine of sigma, and therefore the two expressions on the right will be equal to each other. So we'll get 2 times sine of sigma, theta plus sigma over 2 times cosine of sigma minus theta over 2. And so this gives us one of our sum to product formulas. So it allows us to start with an expression like sine of theta plus sine of sigma on the left with two different angles inside, and write it as a product of two trigonometric functions. Okay, so we can use this, we can do the same thing with cosines. We're not going to go through the whole process. I'll just give you the formula here as we write down our sum to product formulas. So we have that sine of theta plus sine of sigma, as we just saw, gives us 2 times sine theta plus sigma over 2 times cosine of, so it actually turns out that it doesn't matter what order you subtract them in here on the cosines, because cosine is an even function. Cosine of negative x is just equal to cosine of x. So in fact, the order in which you add up these two functions, sine theta and sine sigma, doesn't matter, of course, and that is reflected in the fact that that numerator of cosine can be sigma minus theta, as we have here, or as we had before, or theta minus sigma, as we have here. If you follow a similar sort of argument, we can get that cosine of theta plus cosine of sigma is going to equal 2 times cosine of theta plus sigma over 2 times sine of, times cosine of that theta minus sigma over 2. So you'll notice that these two formulas are very similar to one another, and they give us a way of turning a sum of sines or a sum of cosines into a product. And once again, you can see some common threads that help us to remember this. Once again, the formula involving sines also involves having two different trigonometric functions. And the formula involving cosines involves having two of the same functions, in this case cosines. You'll also notice that the angles that we work with are the same in both cases. There's lots of similarities here. In fact, as I said, the sum-to-product formulas and the product-to-sum formulas are really just the same equation rearranged in a certain way. Now, there are a couple of things that these formulas don't directly address. The first one is what happens when you have a sine theta plus a cosine sigma, something like this. Well, we're not going to have a formula for that type of expression right away. Unfortunately, we don't have an easy way of using the formulas that we just had in order to figure out what an arbitrary sine of theta plus cosine of sigma is. But the thing that we can do is handle differences. So these formulas tell us what happens when we have a sum of formulas, but what happens if we have a difference? So what about something like sine of theta minus sine of sigma? Now, the book lists out two more sum-to-product formulas involving the differences, but I find that more trouble than it's worth. I find it better to just memorize these sum formulas like we have here and handle differences by remembering how the sine and cosine functions interact with negatives, as I mentioned up above. So what we have is that sine of negative x is always equal to negative sine of x, and we have that cosine of negative x is always equal to cosine of x. So this is going to allow us to take sine theta minus sine sigma and handle things directly using this formula. So we have sine theta minus sine sigma is equal to sine theta plus sine of negative sigma, because our formula for sine means that we can move negatives from the outside to the inside of the sign. And now we can apply the sum to product formula here using theta and negative sigma. So we can say that this is 2 times sine of theta plus negative sigma over 2 times cosine of theta minus negative sigma over 2, which gives us 2 times sine of theta minus sigma over 2 times cosine of theta plus sigma over 2. So the point is that in applications, while you can memorize this as another formula, you can also just remember the formula for a sum of sines and move the negative in using the properties of the sine function. Now, unfortunately, the similar expression for cosine doesn't help us to work out a difference of cosines, because we don't actually wind up with a negative on the outside of the cosine function. Minus cosine of x doesn't have a way of rewriting it the way that negative sine of x does. So we do need another formula for cosine sigma minus cosine theta minus cosine sigma. So I will write that down here. We have that cosine of theta minus cosine of sigma is equal to, now this one is a little bit different. It's negative 2 times sine of theta plus sigma over 2 times sine of theta minus sigma over 2. This one's a little bit different, doesn't follow quite the same pattern. However, there are some things that you can look at. Because we're dealing with cosines over here, that corresponds to dealing with the same function on the other side rather than two different functions. We're still dealing with the angles of theta plus sigma over 2 and theta minus sigma over 2. The only difference is that we've got a negative 2 in front rather than a positive 2, pardon me. All right, so let's do a couple of simple problems involving this, but then we'll see how we can use the sum to product formulas in order to solve equations. Let's express cosine of 2x plus cosine of 5x as a single term. Well, we've got cosine of 2x plus cosine of 5x, and we can recall our formula. We've got that cosine of alpha plus cosine of beta is equal to 2 times cosine of, let me not use alphas and betas. Let me be consistent with what I was doing before. Of course, you can use alphas and betas here, but I want to remain consistent. We got 2 cosine theta plus sigma over 2 times cosine of theta minus sigma over 2. So this is going to give us 2 times cosine of, now theta here is 2x, sigma is 5x, and we're dividing by 2, and then cosine of 2x minus 5x over 2. From here we get 2 times cosine of 7x over 2 times cosine of negative 3x over 2. And so that's how we can express a single or a sum of cosines using different angles as a single term involving a product of trigonometric functions, product of cosines. And again, just like we did before, that's the basic idea behind this kind of problem. If all you're trying to do is to simplify a sum or product, or a sum into a product, then it's simply a matter of applying this formula. But let's see an application. Let's solve the equation cosine of x equals cosine of 3x. Let's find all of the x values, where all the angles that we could plug in, where cosine of that angle equals cosine of 3 times that angle. Now this is one where it's not immediately obvious that we need to use the sum to product formula. However, what we can do is the following. We can subtract cosine 3x from both sides. Once we do that, we get that cosine of x minus cosine of 3x equals 0. And here's where we can use our formula. So we have that cosine of theta minus cosine of sigma is equal to negative 2 times sine of theta plus sigma over 2 times sine of theta minus sigma over 2, just applying the formula from before. So here we've got that theta is x and sigma is 3x. So that means we can replace this whole left-hand side with the expression negative 2 times sine of x plus 3x over 2 times sine of x minus 3x over 2 equals 0. So let's simplify this down a little bit. We've got negative 2 times sine of, that would be 4x over 2 is 2x, and then times sine of x minus 3x over 2 would be negative 2x equals 0. So now we're trying to solve this equation where we've got negative 2 times sine of 2x times sine of negative 2x equals 0. Well, now we have a product of things equaling 0, so that means that we have that either sine of 2x equals 0 or sine of negative 2x equals 0. And those are things that we can solve. Now, sine of 2x equaling 0, we want to know when sine of an angle equals 0. So let's take a look at the unit circle. And we know that sine is going to equal 0 at these 2 points on the unit circle, 1, 0 and negative 1, 0. Now the angles corresponding to that are 0, pi, 2 pi, 3 pi, and so forth in the positive direction, and then negative pi, negative 2 pi, etc., in the other direction. So we have that sine of theta equals 0 if and only if theta is equal to pi n, for n an integer. So sine of theta is 0 if and only if theta is a multiple of pi. So coming back over to our equation sine 2x equals 0, this happens exactly when 2x equals pi n, for n an integer. And since we're solving for x, we'll divide both sides by 2, and we'll get that x is equal to pi over 2n for any integer n. That's one of our solution families. And then similar over here, on the right, we have sine of negative 2x equals 0. Well, we know that sine of an angle equals 0 exactly when that angle equals pi times n for some integer n. So this means that negative 2x equals pi n for some integer n, and dividing by negative 2, we get x is equal to negative pi over 2n for n an integer. Now in this case, as it turns out, we have gotten actually the same family. Because n, the number n, is allowed to be positive or negative, finding all of the multiples of pi over 2 is exactly the same as finding all the multiples of negative pi over 2. So these two are actually the same family of solutions. So our answer, our final answer, is either one of these families. I'm going to go ahead and pick the pi over 2n, x equals pi over 2n for n an integer. And that's the basic way behind how we can use the sum to product formulas to solve equations. If we can take an equation that we're trying to solve and rearrange it so that we have 0 on one side and a sum or difference of sines or cosines on the other side, we can use the sum to product formula to turn it into an equation we can solve using the zero factor theorem as we did here. And that's probably the most important application of these formulas for what we're going to be doing immediately in this course. It allows us to solve equations in an efficient way.